Okay, up next we have 20.2, fronts and lows. Vocabulary list is right there on the left. Front, cold front, warm front, occluded front, stationary front. We have two objectives: describe the weather conditions associated with the different types of fronts, and then describe the life cycle of a mid-latitude low. Big question here is, how do fronts and lows influence weather at mid-latitudes? A couple key ideas: the movements of fronts and as well as the lows greatly influence weather at mid-latitudes. Now, a front is a band of air between opposing air masses. Don't forget what an air mass is. It's uniformed characteristics, so same temperature, same humidity. And so scientists classify a front based on the temperature of the advancing air mass. Cold fronts and warm fronts are the two most common. So if you're looking at an air mass and you're looking at a weather map, such as this one right here, you can see that that blue arrow is the advancing cold air mass. Let me ask you a question. Why do you think that warm air mass, why are the red arrows going up? Because they are less dense. Now, if you look at the frontal surface, isn't just a nice big straight up wall. Notice how it curves along. Right here, it curves along in between the two air masses. This entire thing is the actual front. But on a weather map, we're just going to look at the front right here along this line, where the first part of the cold air mass is coming in contact or opposing the other air mass. So at this front, warm air is being forced to rise above advancing denser cold air. That cold air is more dense, warm air is rising because it's less dense. So what happens to the warm air mass as it rises? Very good. The temperature starts to decrease. And assume the warm air contains moisture. Describe what happens next. You're going to have to think way back in this unit, a couple chapters ago. Starts with a C. Condensation begins, so as the air rises and cools, the water vapor in the air condenses and forms clouds. Now, how would the steepness of the frontal slope affect the process of this cloud formation? So if we kept this area right here and we see this slope right here, what if we made that steepness sharper or less steep? So more steep and less steep. What do you think would happen? Now, along a steep slope, warm air is forced up sharply upward, so the clouds would form more vertically, like the cumulonimbus clouds. They can form up more easily than along a gradual sloping front. Now, cold fronts are boundaries between advancing cold air masses and the warm air it is displacing. The cold front on a weather map is blue triangles. They point towards the direction of an advancement. So anytime you look at a weather map, whatever direction that the little blue flags are forming, little blue triangles, that's the direction that it's moving. Now, more dense cold air forces a warm air upwards, steep slopes and possible heavy precipitation moving relatively quickly. This is a characteristic of a cold front. This is the type of weather you'll see at a cold front. So if you're looking at this diagram here, you have the cold air advancing, pushing up that warm air. Look what forms right there. And on the other side, we have a nice big warm air mass right in the middle here. There's a cold air mass that is moving in this direction, and then a cold air mass moving in the same direction, but there's a warm air mass in between. So you have a cold air mass moving down, but then we have a warm front because the cold air mass is moving away from the warm air mass. So that would be a warm front. The warm front, or the warm air, is advancing on this side. Notice the difference in clouds though. What kind of clouds are those? They look like anvils. There's precipitation, they're gray down here. Those would be cumulonimbus. How about these? They look like the slope of the front is not as steep as it is over here. And these are layered clouds. It looks like precipitation down here. Nimbostratus, very good. So the movement of the cold front and the movement of the warm front. Warm fronts are boundaries between advancing warm air masses and displaced cold air masses. So we see a warm front on this side. Advancing warm air rises above the cold air, first signs of high cirrus clouds, and then cirrostratus, and then finally stratiform clouds. Heavy nimbostratus clouds may form and can stretch hundreds of kilometers. Now, occluded fronts are when the cold air front, or the cold front, catches up to the warm front. So let's say that this cold front right here starts to advance quickly, faster than the warm front, and it actually catches up to that warm front. So warm air is forced to rise, and as it cools, clouds and precipitation may form. On a weather map, you might see this right here where the triangles and the little circles, semicircles, are facing in the same direction. And if we do have a color map, it'll be purple in this case. So the occluded front is symbolized like this on a weather map. Now when a front is not moving forward, it is called a stationary front, and that's what we have right here. Now warm air rises over the more dense cold air, resulting in cloud formation and precipitation. If it remains stationary for too long, flooding can occur because of the downpour. So on a weather map, you'll see that the triangles and the semicircles are opposite directions, and they'll alternate between red and blue on a weather map if it's colored. Now how does the movement of warm air vary along a cold front and a warm front? Pause it, answer the best you possibly can. Now along a cold front, warm air is forced sharply upward by advancing cold air mass. Along a warm front, warm air slides gradually over the retreating cold air mass. Now how does the area of precipitation vary along the two fronts? Precipitation falls over a narrow band of ground along a cold front. Along a warm front, precipitation extends over a wide area. So you can see right here the thunderstorms, sometimes more intense than what you'll see at a warm front, but these cold front clouds are very thick, very high cumulonimbus clouds. Over here they're stretched out, and so you might have a larger area getting precipitation, but it might not be as intense. Now fronts are usually connected to mid-latitude low-pressure systems. This is a radar image of the eastern United States showing the weather associated with the low-pressure system. I want you to think way back to the Coriolis effect and the global wind patterns. You remember how everything in the global wind patterns was dictated by the Coriolis effect, and so now we're going to get into the weather systems where we can actually see how the Coriolis effect can start deflecting the air. Now, upper level airflow influences the convergence or divergence of air into and out of pressure systems. The movement of fronts and lows greatly influences the weather at mid-latitudes. So, if we look at this diagram here, it first starts when the conditions are favorable. Surface air pressure at the polar front drops and a wave forms on the front. The pressure is lowest at the peak of the wave. So you have this frontal wave where you have a warm air mass and a cold air mass rotating. And so right here you can see this line right here. This is a cold front advancing in this direction, and that warm front is advancing in this direction. Now the second part here, in the northern hemisphere, winds blow counterclockwise around lows. So right here we have a low pressure system where the two meet. So we have a low pressure system, and as the central pressure continues to drop, and remember, pressure, think pressure. If it's low pressure, that means the air is rising. Okay? So that warm air is being pushed up. Warm tropical air on the east side moves northward, and cold polar air on the west side moves southward. So you have that warm, moist air being pushed up north. What's going to happen? The temperature is going to drop. Now the quicker moving cold front eventually catches up to the warm front. What did we call that? That's an occluded front. Notice how we see an occlusion right here. That's an occluded front. Now the resulting occluded front, at that point we might see the storm intensifying at this stage. Eventually the system will lose energy and begin to weaken after condensation begins to decrease, and we don't see as much movement of that rising warm air. So question, what happens to the warm front as it moves northward? Look at the different stages. Stage 1, you see the warm front here. Stage 2, and then stage 3. It moves over cooler ground and takes on the characteristics of the new surface. Thus, the temperature of the air decreases. You can also say that the moisture may decrease as well. How might this affect the storm's strength? There no longer are sharp temperature differences among the air masses, so the storm will eventually weaken. And that includes the winds. Remember, if there's sharp decreases, then you're going to have an increase in wind strength. If those, if the isobars and isotherms start to get farther apart, then the intensity decreases. Now, where would you expect to find the strongest winds and heaviest precipitation? Look at the different stages, look at the locations. At or near, near the cold front. Where would you expect to find the clear skies? Behind the cold front. So we have this warm air being pushed up. We talked about those cumulonimbus clouds forming there before, and that's where the major storm occurs. And then behind it, it'll be nice and clear. Now, if we're looking at the upper troposphere, so that's looking at the surface, what's happening on the surface. We're going to move our way up into the troposphere because that's where all the weather on the planet occurs. Now, we have something called a trough. Now, the trough is the upper level flow when it's similar to cars slowing down and getting closer as they converge, as they're approaching a traffic jam. That traffic jam is the trough. Now, they speed up and get farther apart, they diverge, and other traffic jams break up. So let's check this out. So we have a high pressure system where air actually is being pushed down towards the surface. Well, this trough right here in the upper troposphere is air moving across the troposphere, the upper troposphere. So you have air coming up, getting on the trough, and then it moves. We have air leaving the trough. So it's like traffic leaving the freeway and then traffic entering the freeway. It's also kind of like how on Finding Nemo, when his dad and Dory jumped on that ocean current and jumped on it and took off with the turtles, and then they got off. So it's kind of same concept, just we're talking about meteorology and we're talking about weather patterns. And next time we'll see you in 20.3.